All right, folks. How are you doing this morning? That good? Glad to hear it. Awesome. Cool. Well, today we are doing great. Good. That makes one of us. No, I'm doing fine. I'm doing fine. I'm doing especially fine today because we get to have our first coding lecture. Feeling good because I'm hearing myself on YouTube. That's not good. Okay. All right. So welcome on Zoom in the class. Welcome people watching from around the inner tubes. So we today are going to be coding dynamical systems in MATLAB. Now, many people have coded in MATLAB in this course before this course, and we're going to be using MATLAB for this course as well, because this is actually, MATLAB is a great language for a lot of engineering computations. Has a lot of features built into it. And it's great for a number of things. So we're going to be using MATLAB today to actually code some simulations of dynamical systems. And so today we're actually going to take the equations of motion of a system. We're going to simulate it, how it moves over time. Okay. And depending how far we get during the lecture period, we'll draw a little animation of it swinging over time. So now's a good time. If you have access to MATLAB, you can pull that up. If you don't have access to MATLAB through either your school or your company or whatever, there's actually a free version called Octave, Octave, that has basically all the features we're talking about today, but it might take a little bit of translating to get it to work, but you can still follow along. Okay, that's the idea of what we'll be up to. So let's get started for today's lecture. So let's simulate. Well, today is the 15th already. The month is half gone. I don't buy it. Okay. And we're going to be simulating dynamical systems. Okay. So you're going to need MATLAB open in just a little bit, but let's do a little bit of an introduction. But the idea is that we're going to be given we're going to be given equations of motion for a system. So once you have those equations, how do you then simulate them? It's an entire field of study to get these equations for whatever field you're in. So if you're dealing with mechanical systems, you take courses in dynamics to figure out how to actually come up with the differential equations you need to then simulate it, right? So you might remember so if you're doing something in physics is too broad. What's specifically called, say, rigid body mechanics. You could use Newton's second law. Second law to basically come up with, say, where the sum of the forces is equal to the mass times the acceleration, and you can use that, right? But it applies to all kinds of systems as well. So we're about to drop your homework 1, where we're actually going to give you the equations for the growth of cancer tumors in the body, okay? And different populations of growth of cancer tumors. And you're going to simulate that because we give you the equations. So the idea is you have what you need is a dynamical model, or the equations of motion. Okay, and typically that's going to be some kind of differential equation. And in our case, it's going to be an ordinary differential equation. Okay, differential equation. So let's simulate a really simple dynamical system, something we talked about last lecture, which, by the way, the new Canvas page is now up. If you go and check the Canvas page now, you can see it's a lot more populated with a lot more things, with a full course schedule for the entire course as to what to expect when. I need to upload more reading materials to it. Those will be up soon for all the upcoming lectures. And it'll have links to all the prior videos. The only thing that's not up is the very, very first lecture video. There's a small technical hiccup and getting that working. So, but I have a backup. I just got to upload it and put it up there. Okay. So for the very first lecture, but last lecture, it's all up there. The stuff that directly ties into what we're talking about today, if you need a review. Okay. All right. So dynamical model. All right. You need an ordinary differential equation. Let's take our example, which was population growth. say a bunch of rabbits. And the idea is you have some population of rabbits, P of t. A rabbit population. This is a dynamical system because it has variables that can change over time based upon either their initial conditions or some kind of stimuli, okay? And right now, we had a differential equation that says dp dt, the change in population over time, is dependent on some alpha times the current population. Now, we solved this just by inspection, okay, and said, hey, we know that the answer is some constant capital C e to the alpha t, right? So alpha, that's right, that's a t off to the side, I apologize, right? I'll move it around so you can see a little easier. So if we solve it, okay, we know that's the answer. So let's plot this in MATLAB. This should be a pretty simple thing to start with. So let's make sure you can see everything here. All right. So that's an example. All right. Okay. So let's go to MATLAB. Okay. So I've just opened up MATLAB. Nothing too fancy here. Okay. So what I'm going to do is, this is just your normal interface that you see. Okay, nothing fancy. This is just MATLAB R2025A. You can't see it in the corner, but most versions, even probably dating back, a decade, would be fine doing the things we're going to do today. The syntax shouldn't change, but it's helpful if you have something reasonably recent in case there is some version skew for different versions of MATLAB. So I'm going to open up a new script. I'm going to click right under where my head is right here. I'm going to click a new script. Okay, new script. All right. All right. Oh, look, a new script. Nifty, cool, neato, right? So in this script, we can write a bunch of commands. It's all going to execute in a sequence, right? And down here, I have the command window. You see that? In fact, I'm going to see if I can. So can you read that? If I say 1 + 1 = 2, can you read that? Or does it need to be bigger on the Zoom feed? I think it's plenty high res for the high definition YouTube live stream, which is at 1080p, I think. Let me just check like the resolution there. Okay, well, then we will make it larger. Okay, home, settings. This is how you make your font larger for when your eyes get worse. Okay, settings. Open them up here eventually. We're going to go under appearance here. Under appearance, you just see fonts. We're going to make our fonts much bigger. We'll make them 26 font. I'm assuming that's a little easier to see. How about that? How are we looking? We can go bigger if we need to. Great. Awesome. So let's see. All right. And so now we can 1 + 1 = 2. We can write commands in the command window, hit enter, and it executes them. All right. Not too bad, right? And also a classic MATLAB command, Y. You can say Y, WHY. Because the bald and excessively not bald and excessively not smart hamster obeyed a terrified and not excessively terrified hamster. Why the fool, the tall and smart system manager. So there's always built-in commands that MATLAB has, okay? Some are more useful than others. One that I find useful is clearing the screen. If I want to clear the screen, clearing the command window, I say CLC. That clears the command window, okay? CLC, enter, boom, okay? Very handy. Obviously, you can store variables. You can say x = 1, and voila, x = 1. And so if you say, hey, what's x + 2? It'll tell you the answer is 3. If you say x + 2 semicolon, it will not output the answer. The semicolon suppresses the result. You don't see what it posts, okay? Right? And you can see off in the corner, it's a little blurry for you. It's really tiny, but there's something over here called the workspace. Okay, that I'm pointing at. And X is stored in there, okay? So you can see what variables are stored on this side of the screen. Okay, everyone following okay? Any technical hiccups? Better, but still kind of blurry? I will fix it. You know what? We're going to do it. We're going to use the nuclear option, my friends. Okay. Now, the YouTube version is 1080p. but we want our Zoom people to see just fine. So we'll go full big screen. So hopefully that's a little better. Thank you for pointing it out. Okay. The workspace. So if you can't see the workspace, what you can go is under View. Okay, and you can check for, let's see, Home. Oh, okay. Trying to find. Normally mine doesn't go away. Oh, here we go. I click Home and the ribbon on the top. It's all the way on the left for me. And I go under Layout. You can always just try. Let's see. And you have layout options. You can click here, Workspace. If I don't want my workspace, it goes away. But if I want it, layout, workspace, and it comes back. It's possible it's hidden under something else. So you want to grab something and move it around. Okay. Right. So right now you can just move your layout around. Okay. I don't use the workspace a lot here, but it's good to know where it is. Okay. All right. So here we go. We've got x plus 2, x plus 3. All right. So we can do a bunch of commands in the command window. And reminding ourselves, we want to model the population growth. We want to simulate this population growth over time. Okay, we're going to create a script now. Okay, up here. I'm going to always like to comment the script. I'm going to call this sim population. Well, now I have command history. I don't want that. Close. Sim population is what I'll call my script. .m. So I'm going to save it. I'm going to save it as sim population.m. The M file is a type of file for MATLAB. Okay. Here we go. Now you can't quite see this super well, but I have over here is my files tab, and my files tab I have simulate population showing up. You want to always put your name on your paper. Christian Hubicki wrote this, and all my friends. That's you et al. Okay, all my collaborators. Okay, here in 2026, 01/15 of the Common Era. Okay. Yeah, and there's going to be some blurriness from the encoding over Zoom. I cannot find a workaround for that. Unless I do a full screen share, at which point it actually makes everything else a lot worse. But you can always go back and watch the playback if there's anything unclear. But I make the text super big so you can see now. Okay, that's the idea. All right. All right. First thing I want to do with any script that I want to run is I want to clear everything. Okay, so that means I like to clear the command window. Okay. So that's CLC. If I do CLC in there, clears the command window like before, right? I also like to clear all the variables in the workspace. I accidentally got rid of my workspace. I'm going to wait. There it is. Workspace. Here we go. Trying to get it to convince it to go into a spot that I can see. Here's my workspace right there. And if I type clear, everything goes away. So if you say x equals 1 comes back. You could also say clear all. It's the same thing, but clear works just fine. So you can say CLC clear. So this clears the command window. This clears all variables in the workspace. I'm typing in comments using just a % symbol here. And close all the plots. Okay, closes all the plots. That way, every time it starts fresh. Okay. And if I run the script again, it's not based upon variables that were stored before. It's just a good practice. Okay. So I cleared everything. Now I'm going to simulate this population using this equation right here. Okay. P of t, your population over time, is going to be some constant c, which is your initial population, times e to the alpha t. And alpha is some constant. So I'm going to define first these parameters I'm talking about. So define my parameters. Okay. All right. First is going to be my population 0, which, okay, I'm going to start with a population of 50 rabbits. Okay. Initial population. And I'm going to have an alpha, which is a growth rate. Alpha, I'm going to say it's it's going to be 2, okay, which is a growth rate. Okay. All right. Okay. And I'm going to define my time final. So which I'll say is 10 units. So the final time. How long do I want to simulate this for? Okay. All right. So now, just to be clear, if we go back to our screen right here. So this C here, if we said that our population at time 0 is equal to some, what we call P0, right? What that means is that P at time 0 is equal to C times E to the alpha times 0. This, any e to the 0 is, of course, equal to 1. Therefore, P0 equals C. So whatever we define as our population at time 0, which in our code was 10, okay, that's going to be what our C is. Yeah, any questions in the audience? I wrote, did I say 50? Oh, I'm sorry, I meant 50. I apologize. Thank you. Yeah, I just highlighted the wrong word. Thank you. I meant 50. Thanks for clarifying. Yes, but anyway, my point is P0 is equal to C. That's what I'm showing, right? So now if we go back to our code, all right, pull up the screen. There we go. So we've got our, so now we want to simulate our system. And because we have an exact solution to our differential equation, it's pretty easy, okay? What we need is a vector of time. So a time vector, which captures a whole bunch of different points in time that we want to know what our population is at, okay? So 0, maybe 0.01, 0.02, et cetera, all the way up to our final time, T final 10. Thank you for pointing that out in the audience, by the way, that I said I highlighted the 10 instead of the 50. Thank you. So quick way to do this in MATLAB, I say, hey, I want to start at time 0. I want to go in increments of 0.01 all the way up to my T final, 10, okay? So this is going to be many increments of time in a vector, okay? And now we want to know what our population is, okay? Our P vector, okay? And at any given point in time, we have a solution. It is, of course, this. It's going to be equal to C, which is P0, as we derived right there. P0 is equal to C times e to the something, and that's exp in MATLAB of alpha times our time vector, our T vector. Okay, this is our population over time. The question in the audience? Okay. Nope. Okay. So people are saying 24 billion rodents. Yes, so it goes pretty. Oh, got it. So you're already ahead of me here. So now we're going to plot. Someone is right. All right. So we're going to plot. Sorry, it's funny. We have some people unmuted in the Zoom, and that's always amusing. So we're going to plot the population over time. So now we're going to plot our time vector as our x-axis and our p vector, our population vector, as our y-axis. And we're going to make it a black line. And the code for a black line is K, and you want to do a dash for a line. Okay? All right. So, and we want to label our axes like good scientists and engineers. Okay? So our time, let's just say, is in years. Okay? This is arbitrary units right now. We didn't derive these crazily, but so population in rodents. Okay, and let's plot it. Taking a second to run the first time. It shouldn't take this long. It's just because I'm running MATLAB for the first time. It's loading all of the utilities and everything. Yeah, Let's see, that's 2.200, that's 25 billion rodents. Okay? Fair bit, right? Breeding like rabbits. Now, in reality, I chose this growth rate to be some arbitrary number. Let's just say it's 1.01 instead of 2, right? And let's take this out. And then it's still hundreds of thousands. Actually, it's over 1 million rabbits after 10 years, okay? Right? So, obviously, it's important to get these models right to get a realistic result. But the point is, hey, look, we simulated it very easily, okay? All right, so I'm going to go back to, let's say the alpha is 1.5, and let's make the time final just 1 year, okay? Just try to make these numbers a little bit more manageable. Here we go. Here we go, okay? Right, so now we have as our, so right now I got this plot of this rabbit growth over time. That easy, right? However, like we talked about last lecture, the reason we can do this so easily is because we have this exact solution to the problem, to the differential equation, which we won't always have. So let's go. So we have a method to simulate systems by not exactly solving the differential equation, but instead approximating the solution to the differential equation. So let's approximate the solution using Euler's method. Okay? Recall that the definition of a derivative, that some, let's say our change in population over time, dp dt, okay, it's approximately equal to a population at time plus some delta t minus some time at t all over delta t. So you make a little change in time. How much does the rise change over the run when delta t is small? That's just the definition of a derivative instead of saying that delta t goes arbitrarily close to 0 in the limit, okay? And therefore, if you solve for p of t plus delta t, which is some next time step, it equals p is equal to t plus delta t is equal to p of t plus dp at that current time t dt times delta t. That's just algebra. And if you want, you can put the delta, the of t up there in the function. I'm sorry, I'll zoom out a touch. There. Okay. Not bad, right? So all we need to do is know what our initial population is at a current time. We figure out what is the current rate of change of the population, then multiply it by delta t, and then rinse and repeat. This is an iterative solution, okay? An iterative solution means you are iterating, which means we will be looping, okay? So let's go back to our code. Right? Okay. So now let's do so you're going to use Euler's method to solve the ODE, the differential equation. Okay. So what we're going to make a couple quick changes to the code. The first of which is I've hard coded this the 0.01 right here. I'd like this to be some variable that we can change more easily because we'll use it multiple places. So I'm going to call it dt for like delta t, okay? And I'm going to say dt is equal to 0.01 right here. This is we'll call this the time step. And that's what we'll call it also on the notes. We'll call delta t, that's a time step. I'll blow it up so you can see a little easier. That's just the time step right there. Time step. All right. So now we're going to solve it numerically. So what we're going to first need to do is we're now going to make a new p vector, okay? We're going to call it a p vector approx. This is our approximate solution, okay? And we're going to, instead of populating it with the answer, since we don't know the answer for all the population growing over time, okay, we're going to just make it a vector full of zeros to start, okay? So we're going to use the zeros command. And you might know that, hey, I can use the zeros command to say, hey, zeros, I want a matrix of zeros with 1 row and 5 columns. And it's that, okay? Number of rows, number of columns. That's how it works. If you said zeros just 5, it'll give you a 5 by 5 matrix of zeros. If you need a review of all this stuff, I put a YouTube tutorial that I made a couple of years back up on the Canvas page. It's all on the front page, and just scroll down and you'll see all the videos. You'll see at the bottom there's a tools video on how to use MATLAB, and we'll cover this, right? However, we want to make sure that this number of zeros is the same size as our t vector. And if we type t vector in the command window, we can see that t vector has 101 different columns, okay? And now, however, that will change if we change dt. So we want to make sure that this vector is always the same size as our t vector. How do we do that? We can actually say, hey, the size of our t vector is size of t vector. Okay. Here, I'll give you an example. If I created a variable, a matrix X, which has ones, and it's a 2 by 2, it looks like that, right? And if I want Y to be zeros, but the same size as X, okay, I can do this. Why does that work? I'll make it a little larger so you can see. It's because the size of X returns this number of rows and number of columns, okay? It's a quick trick, okay? This is what we call pre-allocating an array or a vector. So it's the right size first, okay? And then we say that the very first element of p vector approx, the very first one, which we grab by saying 1, open parenthesis 1, well, that first population, it's our initial population, right? It is this. It's that P0, that C. We have to know our initial conditions. We have to know where we're starting in order to know where we're going. That makes sense, right? Everything tracking so far? Can someone give me a thumbs up if this is tracking okay? Okay, good. Got some thumbs up. Perfect. Thanks so much. All right. So the p vector, your initial population that's approximated is equal to P0. That's you want to set your initial population, right? And back down here. Great. So now we're kind of set. So what we need to do is we need to loop our Euler stepping. And the way we're going to do a loop is with a for loop. And in MATLAB, you would say for, and you have some variable. I like to call the variable iter. A lot of people like to use the variable I. I don't always recommend that in MATLAB out of habit, because I in MATLAB already has a value built in. Okay? It's the imaginary number, I. If I say I, hey, look, it's actually the imaginary number, just like the square root of -1. See, if I say I times I squared is -1, because the square root of -1 is I, right? So I like to use iter instead. It won't break your code unless you want to use the I as an imaginary number. Then it actually absolutely will. Also, electricians like to use J. Sorry, electrical engineers like to use J, not electricians. You're not any electrical engineers listening. I'm sorry if I offended you. So for iter is equal to 1, you want it to count up from the very first time point. Let me just draw it here, okay? Where we're going to do Euler's method is we're going to start at some time and some population. We have some population P0. That's our initial time point. We're going to step forward to the next time point, to the next time point, to the next time point. Boom, 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 boom. We have to step forward once, twice, 3 times. And let's say that there are capital N time points that we want. Here's 1, 2, 3, up to N. Okay? So the number of steps that we're going to have to make is 1, 2, 3, 4, 5, 6, 7, 8. You might say it's N. Well, it's actually not quite N, because let's say it's actually 1 less than N. Why is that? Because imagine if N was 3. So let's say N is 3. There are 3 time points. Okay? So 1, 2, and 3. How many steps do you have to take to get to the end? 1, 2, right? So it's actually, the number of steps you want to take is N minus 1. Okay? So back to our code. We want to take N minus 1. And you said, Dr. Kubicki, Christian, what's N? We have to define what N is, right? There's a N is the number of time steps. So the way we get that number is we would say, hey, N is the number of elements in our time vector, or T vector, right? That's it. Okay, that's the number of elements. That is not a number 1, that's an L. I tried to pick a font where that L is a really obvious, really obvious L, because sometimes a lowercase L looks like a number 1. All right, so we're going to iterate from the number 1 to the number N minus 1. That's the number of time steps we're going to take. Okay, now we're going to use Euler's method. We're going to use this equation here. Okay, where the next P, so P vector approx, iter plus 1, because the current one that we have is iter. So we're on so if we're on iteration 1, the next one is going to be 2, right? We're going to make it equal to, I'm going to do a little dot, dot, dot to save some space, dot, 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 and ellipsis, and you hit enter, and it'll continue the line down to the next line with a little indentation, is equal to this dp dt. Well, what is that? Well, our dp dt is alpha p of t, the current alpha times the current population. So, sorry, I jumped ahead. I'm sorry, I jumped ahead a step. I skipped over this right here. So the current population, so it's equal to P vector approx iter plus dp dt. Now that is alpha times the current population. So alpha times the current population, P vector approx iter. Boom, semicolon, so it doesn't output. Oh, I forgot the little ellipsis here. See that? We're all good? So the only reason I had to put it on 3 different lines is because the font is so huge. Okay, but hopefully it's good enough that people can see. So we have our Euler step loop, and I have to finish off the loop with the end command here. Okay. Now once I do that, I would like to plot on the same plot we had before the solution to our approximated vector. Okay. So I'm going to want to do a whole other plot. Now, one thing you might know in MATLAB is that if you just plot again, it'll blow away the other plot and erase it. Okay. And in order to prevent that, you put on a hold. You say hold on. Okay. This prevents new plots from erasing prior plots. That's what, yeah, what you got? Yes, you're absolutely right. We got to multiply by dt. Thank you so much. Applause to you. I was so enthralled with myself that I forgot. Thank you. Anyway, so let's go down times dt. What someone in the Zoom pointed out is I forgot to multiply by delta t, which is dt. Thank you. So we just added it there. Thank you. All right. Okay, now we're going to want to plot our new plot. So plot, and we're going to have our time vector. The time vector is the same. However, we have our p vector approx, and we're going to make it a red dashed line. So that way it can be like, if they overlap too much, we can still see the red and the black if they overlap. And the way you do red is you say red with an R, and dash dash is a simple dashed line. Okay. We're going to do a hold off just for good habit, and we're going to run it. I hit F5 to run my code. You can do what you want. Okay. Running my code, running everything. Okay. Now, you might not be able to see it. It was a little blurry probably on Zoom, but is anyone seeing lines that are super kind of very similar? Anybody seeing that when they code their code? Yes, I'm seeing some thumbs up. Is it exactly the same? Anybody? Does it look exactly the same, or do you see any difference? Because I see a little bit of difference. So one thing, these lines are a little thin. I'm going to make the lines thicker. This is just a good MATLAB trick. I'm going to go to where I do my plots, and where I define my little plot, my little plotting elements here. I'm going to say I'm going to add another argument to plotting. I'm going to say plot line width. It actually gives me the option in the autocomplete there. It's perfect. And change it to 3. So it's just nice and thick for you all. Okay. I'm going to do the same. I'm going to copy this. I'm going to do the same thing with my other plots. Okay. So both of my plots, I'm going to put line width right there. Okay. Like that. I'm going to run it again. There we go. They are slightly different. Okay, but they followed about the same, and and of course they're gonna be slightly different. Why? Because this is an approximation. Okay, and the way we set up our code is actually pretty convenient. We can change we can change a few things. What's something that would make this approximation maybe a bit better? Anyone want to guess? You would change the time step. It's fine. That's great. You want to make the time step smaller. Because, again, this is an approximation that depends upon delta t being small. Delta t is small. So if we made it bigger, it would be worse. So I'll show everyone if I make the time step up here 0.1. Let's see it be worse. Significantly worse. You can see that's very different, right? Okay. Now let's change it to 0.0001. Sorry, 001, 2 zeros. Look, that's pretty dang good. Right? So obviously, the smaller you make your time step with an Euler's method, the more time it might take to run your simulation. Here, this is a super simple one. It doesn't really matter too much. Okay, but I do want to point out that Euler's method is quick and it's dirty, but it's also like the worst of the approximated ways to approximate your dynamical system, the solution to your differential equation. There are higher order methods. This is what we call a first order method because it uses the first order derivative. There are better ones, and some of which we will use, especially when we're using trajectory optimization methods. Okay, there's some fancy ones that we're going to use. There's things like Hermite-Simpson. But it's what we call an explicit method because it only takes data from the past in order to predict the future, which seems to make sense. How can you predict the future without the future, or with the anyway? It's weird. How can you use the future to predict the future? But that's a strange. But there actually are methods that do that. They're called implicit methods, and we will use them, and they're actually super handy for optimization. Okay, so we'll get to that in several weeks on the calendar. Okay, but it's really neat. Okay, so we can do Euler's method with this model. Let's add an additional layer here. One where we don't use Euler's method. We use So let's use a Runge kutta method, okay? And there's something we like to call there's a whole set of ODE solvers in MATLAB. And if you ever want to find out how anything works in MATLAB, you can type help and the command that you want to try. In this case, it's help ODE 4.5. Okay. Okay. Now, the 4 and the 5, it's not 45, it is 4.5, because these are the order of the approximation of the Runge kutta. I talked about how Euler's method is a first order method. This is a fourth and a fifth order method together, okay? And the idea is, one thing that's really cool about it is that who decided that time step that we just did? You know, obviously we did. we just decided it, right? How did we decide it? Like, put our thumb in the air, like that's pretty good. We looked at the result, and we actually were able to compare it to the result that we know it's correct. But in the future, we're going to have simulations that we don't know what's correct. So wouldn't it be great if we had something to select the time step for us? And that's what ODE 4.5 can do, okay? Now, and further, ODE 4.5 doesn't decide just one time step. It can also decide to change the time step midstream. That if there are points where the simulation is really accelerating quickly, it will make the time step smaller so it's more accurate. And if there are times where it's not changing very much, it'll lengthen the time step to save you time and computation. Pretty cool, right? So this is how it works. ODE 4.5 solve non-stiff differential equations with a medium order method. This MATLAB function basically takes in a range of times, time zero and a time final, integrates the system of differential equations defined by this. This might look familiar. This is just a different way of writing what we wrote last lecture. Okay? Where we wrote, and I'll watch here, where we said we wanted our state vector x dot of t as being some function of x of t. Okay? Right? We wrote that. Now, if you look at that's what basically that is right there, except it also asks for time. It's saying the derivative of y, which is your state, is dependent upon y and your current time. So the way it works is you have to give it a function that you take in the current time and the current state, and you tell it the derivative. Okay? And then you give it the time span and the initial condition. And then it gives you a whole bunch of time steps and the state out. Okay? Right? So let's use that really quickly. So what we need to do is we're going to use a question in the chat, when are we going to do some stability analysis? We're going to cover stability analysis when we get to LTI systems, which will be, I think, in about 2 weeks, and it would be linear stability analysis. The degree to which we need to cover nonlinear stability as an analysis standpoint would be near the end of the course if we talk about safety critical systems. We'll talk which cases we would touch on a little bit of Lyapunov theory and how, but specifically in this course, we're using optimal control to stabilize our systems. So we're doing the controls part, the control part, which results in stability. So good question. We use ODE 4.5 to simulate this system. Okay. So what we need to define, our dynamics as a function where we need to define our x dot dxdt right there as being equal to some function of time and your current state x. Okay. Now, my friends, we did a little bit of state space analysis before. Just off the top of your head, anyone want to guess, applying our method that we used, how many states we would need to represent that differential equation? Anybody? We'll get to this again. Well, thank you for the question. We only need one. It's the first order differential equation. We're only going to need one. Okay. So what we need to do is define a function. So we're going to call this function call it dynamics. And there's a way you can define a function as not a file in MATLAB. You can define it just as a line of code, okay? You can say, hey, I want this dynamics function to be a function that takes in two things. And you use the @ symbol. And you say, I want it to take in two things, time and state, x. And what does it send back? It sends back the derivative with respect to that state. So our state is going to be p. Okay? So it's the only state we have, and it sends back alpha times x. So this part here, that's the derivative of our only state p, right? That is right up here, right? The derivative of p with respect to time is equal to alpha times p. So where p is our only state, x. Okay? We have to just define our dynamics as a function like that. Any questions about that? That's a little tricky. Okay? Once you know how to do that, you can do it. Makes simulating really simple. Okay? All right. I'll show you how simple. We're going to create a new t vector. We're going to call it t ODE45 because ODE45 is going to define the time vector. Okay. And we're going to have our state out, which is going to be our x. So we're going to say here that where t is time and x is state vector. X ODE45 is equal to ODE45. We're using this syntax right here. And we want to give it our dynamics, our ODE. We call this the ODE function. We call this our dynamics. We want to give it a time span. And the way to define a time span is a vector with your time 0, which is 0, and your final time, which we call t, what do we call it? T final, right? We're running out of space, so I'm going to do a comma, ... And what else do we have to give it? An initial condition. So we need an initial condition for our state, which is our population, which is P0. I can fit that all up there. That's not bad. P0. Semicolon. So here is going to be a vector of all the time points that ODE45 uses. And here is going to be a vector of our state coming out. Okay. It's going to be a column vector. We'll talk a little bit more about what ODE45 does. Okay. So we're going to hold on. We're going to put hold on our plot. Hold on plot T ODE45. Then X ODE45. Okay. And we're going to make this a blue, and we're going to have it be a line, but we're also going to put little X's where the time points are. Okay. All right. So, and we're going to hold off and see what happens. Okay. Now, right now, it might be a little hard to see on even my plot here. So let's see if I can make the X's larger. So I'm going to say X, I'm going to change the marker size, comma, marker size. I'm going to make this marker size 10. I think that'll make it larger. It's a little larger. I'm going to make it even bigger. I'm going to make it 20. Here we go. Okay. So here we have all of our simulations. They all overlap really nicely. But the difference is that all those X's, those are the time points that ODE45 chose, and it chose them itself. Okay. And you could probably see there's probably there might be a little bit of difference in what those time steps are. I'm just going to check to see what those time step differences are. T ODE45. I'm just going to use the diff command to figure out what the difference is between each of the times in that vector. Just a little, it realized, hey, we don't have to change the time step at all because it's just it is just a smooth exponential, right? But if we had a really oscillating system, okay, then sometimes it might have to change it a lot. Okay, we did it. So we simulated this population in two different ways. Any questions so far? The ODE45 one's a little tricky. Don't be afraid to ask questions about it. And when you see any code, want to take a swig of this coffee? Okay. So the trickiest part is defining this dynamics function, which requires putting your system into this form. Anyone remember what that form was called? It was state space form. For a nonlinear system, it's in state space form. Or any system that could even be nonlinear. Right? Nifty. Cool. Let's do a system that's a little bit more fun. Omari, you have a question? Yeah, you got it. So this is what we call an inline function. So who here, raise your hand if you've made a function in MATLAB before. Anybody? Okay, Conrad, if you don't mind, anyone who want to pop in and say, how did you make a function in MATLAB? Because this is worth me spending a little extra time on. Anybody? Did you make a new file to make a function? Give a thumbs up if you've made a new file to make a function in MATLAB. Anybody? Great, someone has. That's typically how it's done. So what you can do is make a new, quote, script or function, right? So let's do it in the more verbose way. This is a great question, Omar. It's worth talking about, okay? Where if you wanted to make that same function, you could say function, where it returns dx or x dot. We'll call it dx, the derivative of x. And we'll call it ODE fun. And it takes in t and x. Right? This is a function that takes in time and state, time t, state x. Right? And we'd say, hey, the derivative dx, so and it returns. Sorry, I'll get rid of that. Apologies, I'm covering that up. And it returns dx dt, which we call dx, right? So if we wrote dx is equal to alpha times x, that would make sense, right? We just have to define alpha here as whatever that was, equal, what, 1.5 or something we wrote above? We have to write it in here as well. And we would save it, and it would be its own function called odefun.m, right? Does that make sense to anyone? Is this the way I just did it right here? That's a MATLAB function. Great, right? And you could change this out. And let's see, was it 1.5 was my alpha? Yeah, perfect. You could change this out, and you could say, hey, I want you to use the function ODE fun that I just defined, right? ODE functions in the same folder as what I just wrote. We should be all good. The only thing that you have to do is you have to add a little @ symbol, because if you don't add this, then this command thinks that there's a variable called ODE function, ODE fun, as opposed to @ODE fun, which says actually it's something called a function we want to use, right? And this should work exactly the same way. And in fact, it does, right? This line here creates an inline function. This is just a much simpler way to do this exact same thing. Okay? It says, I want to create a function called dynamics. And what it is this is called a function handle with the alpha, with that little with the @ symbol, and says, this is what I want to take in, and this is what I want to spit out. So this is a much more compact way to write a function. So you didn't have to just make a whole new file for this. And that's not just annoying, it's just I had to make a file. I also had to tell it what alpha was inside of this file, because as we all know, inside of this function, it doesn't know anything other than the variables that get sent in. And it doesn't know what alpha is. Okay? In fact, so it's actually cleaner because here we know what alpha is because alpha is defined in this exact same function. Does that add a little bit more clarity to that, Omari? I hope I didn't over-explain that or under-explain that. Thank you. I try. Awesome. But that is tricky. It is worth the time to explain because that throws people off. And it's just so clean. Look, it's all one line of code. Oh, it's so nice. It's so great. So cool, right? Now, let's do a different problem. Let's finish one. Let's do one that we talked about last lecture. Okay. So let's do an inverted let's do it. Let's do a pendulum. A pendulum under gravity. Now, last lecture, we derived the equations of motion for a pendulum under gravity. I'll draw it out real quick. So we have our pendulum. We have some vertical line that the angle with respect to that vertical line there is theta of t. We have some length of the pendulum, and there's some bob, on it with mass m, and you got gravity pointing down. Okay? And we found it, and we derived, we're using just first principles, using a free body diagram and summing all the torques on this pendulum. It's that you come up with that theta double dot of t, which means that it is the second derivative with respect to time, is equal to minus g over L sine of theta of t. Okay? That's it. Now, this is not a first order differential equation anymore. It's in fact a second order differential equation. Okay? Which means that we have to think more carefully about the state space. We now have to put this in state space form using our patented method. What's our patented method? Well, first thing that we do is we find the highest order derivative, which is 2. We find our lowest order derivative, which is the 0th order derivative, theta of t, for all of our variables. And sorry, I don't know what so therefore 2 minus, which is 0. That's the 0th order derivative. I apologize. And you subtract them, and it's 2. And there's no other time varying quantities, independent time varying quantities that we don't control directly. So as a result, there are going to be 2 states. What are the 2 states? Well, we'll put them into a state vector. We'll call it x of t with a little hat because we'll call it a vector today. All right. And there's 2 states. And we're going to start with the lowest order derivative, which is theta of t. This is the process that we went through last lecture, theta of t. Then we step up to the next highest derivative, which is going to be theta dot of t. And then we step up to the next highest derivative, which is theta double dot of t. But we said, oh, no, we don't use the top one. We don't use the highest order derivative. We stop there. We stop one before. Okay? That's our state vector. State vector. Then we write the state vector's derivative. So x dot of t, and that's just taking the derivative of everything inside of the state vector. And then we rewrite each of these elements in terms of just states. Okay. Also constants, also any control inputs that you have, those are fine. But you can't rewrite it with something like this that isn't a state, because theta double dot is not a state. Okay. Now theta dot, how do we write that in terms of states? It's super easy, because theta dot is a state. Oh, how nice. Theta dot of t is a state. What about theta double dot of t? Okay. Well, we have an equation for it right there. Minus g over L sine theta of t. Theta of t is a state. It's right there. State. And all this stuff, that's fine. Constants, operators, all cool. Minus g over L sine theta of t. Making sense? That's the process we went through. So now we have this in state space form. So we have some x dot of t is equal to some function of x of t, right? State space form. X dot of t, and this is some function. Oh, forgot the end of the t right there. Good. That's simple. That's the process. Now we can code it up. Let's code it up using Euler's method in a whole new script, okay? Because now we have to apply Euler's method to these two orders of differential equations, right? Okay, so let's go back to the board here, back to the code. Let's make a whole new script, all right? Make a whole new one. Okay, so we're going to make this, see if we can do a, we'll call it sim pendulum.m. I'm going to save it as a .m file, sim pendulum.m. Done. Put our name on our paper, Christian Kubicki and all my friends, 2026 01 15. And when you all jump in and you correct my code, I am happy. So when you find things, I'm doing this all on the fly, right? Right? With an audience. That's fun. And we're going to clear everything. We're going to clear the screen. We're going to clear all the variables. We're going to close all the plots. Notice I just put them with semicolons in between, so it treats them like they're all new lines. Great. Thanks for tuning in there on YouTube. Really appreciate it. All right. So now we have to define our parameters. Let me just turn this over here. Define our parameters. What are our parameters? Well, let's pull them up again. Our parameters for our pendulum, there's three that I see. I see m, which is not even in our equations of motion. It gets canceled out for when there's no forcing on the pendulum. There's the length, and there's gravity. We're going to use SI units, international units. So that would be, let's just say our mass is a kilogram in case we want to use it later. We're not going to use it today. Let's make our length just be 1 meter. Okay? This our mass is 1 kilogram. And gravity is equal to 9.8. And that's in meters per second squared. Okay. All right. Other parameters we want. We want our time final. Okay? Let's say our time final is 10 seconds. And we're going to use Euler's method. So with Euler's method, we're going to say dt is equal to 0.01. Okay. All right. So we're going to simulate using Euler's method. Okay. So we're going to pre-allocate our vectors. So we want our time vector. So we'll call it just tvec, just to save ourselves a little time. So we 0, dt, t final, done, semicolon. Okay. All right. Stop me if you catch anything. All right. So we want to, but now we have to not only keep track of just one population, one variable, we need to keep track of every one of our states. Okay. And it's actually going to make me realize we have to include a few other parameters, but we'll get that, well, kind of other variables, I should say. We have our two states right there, which are theta and theta dot. So we'll call it a theta vec. It's going to be a vector of all of our thetas, okay? And it's going to be, we'll pre-allocate it to be zeros of the same size as our tvec. Okay? Just like we did before. So it's the same size. And this theta with respect to t, we'll call that d theta vec, the derivative of theta vector, which make it also zeros of the same size as the tvec. People following along okay? They were able to get the last result all right? Okay. Nifty neato. All right. So now the one thing we also need, we need the initial conditions for every state. That's important. You need an initial condition for every state. You can't know which way the pendulum's going if you don't know which velocity direction it's going, right? At the beginning, or how fast it's going, right? Just like you have to also know the initial position. So I'm going to say that I wanted to start, if I gave it an angle of 0 per this chart right here, right? If I gave it an angle of 0, it would be vertical down. Okay, the way I define that angle goes that way from the down. However, if it's 45 degrees, it's going to end up right there, positive 45 degrees. And that's pi over 4 in radians. So I'm going to call it theta 0 is going to be pi over 4. Okay, that's like 45 degrees, right? Okay, and d theta 0, our initial speed, I'm just going to say it's 0. And this is going to be in radians, and this is going to be in radians per second, right? Not too bad. Nothing too crazy here. All right, now we can actually do the Euler. Oh, so I guess I can now finally simulate the Euler loop. We're going to do 4 iter. The for loop is going to be 4 iter, 1 colon, the number of elements in the tvec minus 1. For the same reasons we talked about last time. We have, if we had 10 time points, we only take 9 steps to go from beginning to end. So 1 less. So we just wrote this as a slightly more compact line. Astute people among you might wonder if this minus 1 will subtract 1 from this number or 1 from the result of this. Keep in mind the colon, just so you know, just makes a vector of numbers. So, but the order of operations in MATLAB is that it subtracts from this first and then makes the list. So, in case you're curious, so that should work just fine. All right, so now we got to do Euler's method. So using Euler's method, okay, we have, let me just go back to the board real quick. We're going to have our 2 different states that we got to update with Euler's method. Now Euler's method is going to be for one of them, so theta of t plus delta t is going to be equal to theta of t plus theta dot, which is its derivative, of t times delta t. And theta dot t plus delta t is equal to theta dot of t plus theta double dot, its derivative with respect to t. And this here, we know is equal to being minus g over L times sine of theta of t, right? Not too bad. So let's write that out real quick. So our next line, we're going to say theta vec. We're going to say the next theta vec, the next theta in our vector, the next one, iter plus 1, all right, is equal to the previous one, theta vec iter, plus, let's make a new line here, its time derivative, theta dot, okay, at the current time. So d theta vec at the current time iter times delta t. Don't let me forget, friends. Thank you. Times dt. Change in time, right? Now the same thing for d theta vec. We're using this equation here. So the next d theta vec, the next one, iter plus 1, is equal to the current d theta. So d theta vec at the current iteration plus dot 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 dot, new line, theta double dot of t, okay, which we know is equal to minus g over L times sine of the current theta, theta vec iter, okay, times delta t. Boom. For loop and the for loop. My friends, we're plotting already. We're going to plot our t vec, and we're going to plot our theta over time. Okay. Now, if we did this right, and again, it's just plotting over time with a little black line, we should start at pi over 4, which is the positive angle for the pendulum, okay? And it should swing back and forth, which means I'll see the angle do this. Wow, 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 wow. All right. So we got to do it for each state. Hopefully, Prasad, I answered that correctly. You got to do it for each state. That's absolutely right. We can plot every state if we want. We're just going to plot just the angle at the moment. So, all right. So we should see it like wobble like this, almost like a sine wave. It's not a sine wave. It just kind of looks like one. Let's see what happens. Uh-oh, nothing moved. Theta 0. Oh, what did I not do, friends? I did not set the first element of the vector to be equal to the initial state. So what does it think? It thinks the initial state is 0. Pendulum starts straight down. Where does it move? Nowhere. So we got to fix that. So we got to say that theta vec 1 is equal to theta 0. And then theta d theta vec, we have to set the initial conditions for both state variables. D theta vec, the first element, is equal to d theta 0. Now we have set the initial value of the angle to something that isn't 0. So now it should hopefully work. Voila. We have something that swings. You'll notice the swings get bigger and bigger, right? Is that reasonable? Is that physical? Is that right? No. It's gaining energy from nowhere. Thermodynamics says that's impossible. Why is that happening? Well, it's because, again, this is an approximation, friends. It's an approximation. So how do we make the approximation more accurate? We already know the answer to this. We got to change dt. Make it smaller. Let's add an extra 0.001 for dt. And let's run it. And voila, look at that swing. I'm going to make the line a little thicker using the line width command here. Comma, line width. Width. And I'll make it 3 so you can see it a little easier. Okay? There we go. Much better. Okay? But again, because we're using Euler's method, we had to guess at the time step. Now, there are better ways, there are more sophisticated ways to choose a time step. And especially when you have higher order methods, there's actually stability theory for having a stable numerical result. But here we're going to use ODE 4.5 to do that. It uses a method called Dorman Prince. It sounds very sophisticated, and it kind of is, but honestly, you can code it from scratch. It's not that complicated, okay, to actually implement. So let's use ODE 4.5 instead. That'll be the last thing we do today, okay? And believe it or not, we are not far away from doing this. We have to define our dynamics using the x dot is equal to f of t and x format, right? So let's go down. We defined this here, right? So what's going to happen is we need to create some dynamics in a function. We say, make an inline function by saying at. It's got to take a function that's going to take in time and state. That's what ODE 4.5 demands that we give it. A function that it can send in time and state and gets back the derivative of both of the states in this case. All right. And what does it need to send back? Well, a vector where the first element is the derivative of our first state and the second element is the derivative of our second state. So if x is equal to theta and d theta, I'm putting this in comments, that internally we in our heads we're saying our first state right here is theta, and our second state is d theta. So it sends in some number of states, 2 states, and the derivative of our first state is actually our second state, right? The derivative, so the derivative of our first state, theta, is theta dot, which is our second state. So the derivative of our first state, x1, is actually x2. Okay? We're almost done. We're very close. Okay? And the derivative of our second state in terms of state is minus g over L sine of theta of t. Okay? Minus g over L times the sine of theta of t. What's theta of t in our state vector? Where is it? It's the first state, x1, right there. So we would say x1. Okay? Guess what? We can say, hey, we're going to call it our t out. We're going to use ODE 4.5. T out, x out is equal to ODE 4.5. We have to send in our dynamics. We got to send in our time span, which is going to be from 0 to what t final we called it, t final, and we have to send in our initial state for all of our states, okay? And so our initial theta is theta 0. I'm going to put a little dot, dot, dot here just because it's going to take up a little bit more space here. Theta 0. And I put a little semicolon just to make it a vector of states, just to keep the vectors to be, vertical for the state vector. I don't think it really matters here, to be clear. And d theta 0 for our second state, right? Those are our two initial conditions, all right? We can break that out. I'm going to stick around. If you have to leave immediately, I understand, okay? We're right at the end, okay? Semicolon. Now we're going to plot the result and come on the same plot, so it's hold on. Let's plot on the same axes. So now we're going to use t underscore out. And now here's the only rub, okay? X out. This is how the simulation is giving us the results of two different states. So the way that MATLAB does this is ODE45 gives you will give you your first state x1 in your entire first column. And it'll give your second state x2 in your entire second column. And if you have more states up to some state x lowercase n, it'll be in the nth column. And this is all your time points in that direction. So if we want to plot the results of our first state, we have to grab the entire first column of this x out that ODE45 is giving us. So we just need the whole first column. So how do we get the first column? We say x out. We want every row in this matrix. Colon gives us every row. Comma 1 gives us the first column. I'm going to make this a red dashed line. Hold off. Plot. You can't even see it. It's so perfect. I'm going to make the line width thicker. We did it. We're done. So line width is 3. And you can see there's a little bit of difference. If I make the Euler time step worse, I'll make it 0.01. You could see the clear difference. I made my time step 0.01 again, and there's the result. That's it. Let me get rid of that so you can't see. We're officially done. I'm a couple minutes over, but we simulated two different systems in two different ways in MATLAB from scratch. Pretty cool, eh? So you're all officially released, but I'm happy to stick around for a few more questions, okay? Anything else you want to add? You too. Thank you. I didn't label my axes. Let me add this to the code. I was a bad engineer. It's going to be our time in seconds. Feel free to pop in with any questions at any time. So we're going to add an X label and a Y label. This is going to be our pendulum angle in radians. Boom. Now we have labeled our axes. Isn't that gorgeous? Right? Okay. So the question is, what's the advantage of using Euler's method over the direct dynamics of the system? I mean, the dynamics of the system are just the differential equation. They are not the solution to the differential equation. Euler's method approximates the solution to the differential equation. If you are able to solve the differential equation by hand or analytically, you don't need Euler's method, okay? But for the pendulum, it's impossible. There's no possible way to do it. There's no equation that you can write down that you can just put in a number and get out, oh, this would be the position of the pendulum 10 seconds from now. You have to approximate it. That's why we use Euler's method and use things like the Runge-Kutta methods inside of ODE45. Does that answer your question? So do you understand? So the key is that we have to solve the differential equation. So you mentioned you having to use the dynamics of the system. Are you suggesting solving the dynamics in some other way? Or what do you mean? Yeah. Correct. So the question is the pendulum impossible to solve because of the order differential equation? No. There are many second order differential equations that you can solve by hand. In fact, in differential equations, you probably have done a few of those. In fact, if you take controls one, you use the solution of those to solve a lot of, to figure out how a lot of systems will converge that are second order. It's that sign. It's that sign here. Let me pull it up so you can see it. Yeah. It's the sign of the angle that makes it impossible to solve. Okay, that doesn't mean any equation that has sign in it is impossible to solve, but this is what we call an elliptic integral. And there is no way to write down the solution to an elliptic integral with just normal functions like an exponential or a sine. And therefore we have to use approximations when we actually want to know the answer. Thank you very much for the question. All right, we'll stop the stream now, and I'll stay on the Zoom for a little bit more. Thanks for those of you joining on the stream today. I really appreciate it. I'll see folks, if people want to join on the machine learning class at 12:30 p.m. Eastern Time, by all means. Take care. Pull up the code in case anyone needs to see it.